It's time to run the study and review the results using the FSAE steering wheel simulation file. We have now done all the work to set up the study. Let's turn off the display of the mesh model, go to the Solve dropdown and select Solve. The dialog will appear listing the options regarding how to solve the study, including the option to solve on the cloud or solve using local processors. As an aside, some of the advanced study styles cannot be solved locally as they are too process intensive, so they use cloud solving by default. In the Active Documents section, we can choose to solve all studies if we have more than one study, or we can simply select the studies we wish to focus on. Next, a status report on whether or not it's ready to be solved, if it's already been solved, or if there are errors in the file will appear. Since we only have one study to solve, we'll click Solve One Study. The Job Status dialog box will now open. We can follow along with the status of the study. The job status can be closed and the simulation will continue to run. When the study is complete, the model will display colors correlating with the legend in the lower right. This legend can be changed to display the results for different parts of the study of the model. On the right-hand side of the screen is a results dialog. For this model, the safety factor is reporting at 15, which is the highest number that will display, and this tells me that if my loads and constraints are correct, my design is overbuilt based on the need for lightweight components in the car. Also in this dialog, we can adjust the default values for safety factor targets, review the recommendations that are offered by the system, we can change deformation display scale, and we can disable the option to automatically see this dialog. If you decide to close the dialog, you can always restore it by selecting the icon with the double check mark next to the study display option near the legend. Looking more closely at the model in the canvas, we can see the display of the original shape with a wireframe and a scaled version of the deformed model. What is displayed in color is an exaggerated representation of what is happening to the model under load. This scaling is intended to make it easier for us to understand what is happening visually. We can change the display by going to the Results dropdown, where we can toggle off and on the wireframe visibility as well as modify the deformation scale to be more exaggerated to show the actual deformation, or we can completely turn the deformation off. Let's use the actual setting. Coming back to the safety factor, at 15 we have a lot of room to refine this design. Based on the results, we could look at changing the thickness of the component, enlarging the cutouts, or making other modifications. Let's take a look at some of the options we have to view the results. Let's change to stress. The screen display and legend will update with the results, and we can choose different types of stress that can be displayed. The default is von Mises, but we can show the results for principal, normal, or shear stresses. The legend on the right displays the minimum to maximum values, and we can limit the display to a specific range using the arrow icons to focus on a portion of the model that falls within the selected range. Zooming in on the area, we can see a concentration of stress around the bolt holes and where the components come in contact with one another. By being able to focus on specific ranges, we can remove portions of the model where there's no concern to more closely look at the areas that need more scrutiny. Let's change the display to displacement. From the initial results display, we know that the plate is twisting around the shaft and on itself, but by switching to this display, we can see the numbers related to the result. The maximum displacement listed is just over 0.002 of a millimeter. This, of course, is very minimal, but we can use the adjustable scale to see what areas fall within this range. We can easily look at other types of results, including reaction force, strain, or contact pressure. The ability to visually review the results makes it easy to not only know what they are, but if we've set up the study properly, get meaningful results. Looking more closely at some of the areas of elevated strain, they seem to be unexpected. The higher strain in the sharp corner of the steering shaft is logical, but showing strain at the edge of where the steering shaft and the base plate meet makes me wonder if the contact sets that were automatically generated should be reviewed. By going to the browser and turning off the visibility of the steering shaft, we can more easily see the strain map on the surface of the base plate, where we see very little strain on the splines, but higher concentrations on the edge of the steering shaft, which would most likely be able to slip on the surface of the base plate. This suggests that we probably need to modify the contacts manually to ensure the correct engagement. For now, let's focus on learning to interrogate the results, navigate through the options, and adjust the display. Let's switch back to the stress display and go to the legend options, where we can choose to turn the legend off or on, change the size, or select whether the display of the results will be banded or have a smooth transition. If you make changes to the display of the legend, it will not affect the actual results, only how you see them.